Okay, this is an example of torque and force on a magnetic dipole. A couple of twists here. Instead of just giving you a loop, I'm giving you a disk with charge Q that rotates. And then the other thing we'll do is we'll look at the force it experiences from the field of another dipole. That basically means a non-uniform field. Let's just first quickly review what we mean by dipole. A dipole moment is a vector. It depends on the current and the area of a loop. So the basis of all magnetism is little loops, even inside of a permanent magnet that's made of a bunch of these little guys. And when we talk about the dipole moment, what we mean is if you curl your fingers in the direction of the current, so on the right side, we go in, on the left side, we go out. If you point your fingers in on the right and out on the left, your thumb will point up. That is the direction of the dipole moment, and it's the current through the loop times the area of the loop. So that's what we mean by that. The force on a dipole points in the direction of increasing B field once mu and B are aligned. What do we mean by mu and B being aligned? Well, there's torque on a dipole whenever it's in any field, uniform or non-uniform. So if you think about permanent magnets, if you point the north ends at each other, you'd say, well, those are going to repel each other. And you're right, they do repel each other. That certainly doesn't seem to point in the direction of increasing B field. But remember, when you put a dipole in a magnetic field, it will rotate until its magnetic moment aligns with the direction of the magnetic field. And once they are aligned, then they will be attracted to each other. That means that now the force is in the direction of increasing field. So this torque in a uniform or non-uniform field, that's the thing that provides this rotational force that gets things aligned. Okay. This is valid for infinitesimal loops. There's some weird terms that pop up if they're not infinitesimal in a non-uniform field. And I just want to compare this really quickly with electric dipoles. If you feel comfortable with electric dipoles, magnetic dipoles are basically all I'm doing is swapping out symbols. So instead of a P, I have a mu, and instead of an E, I have a B. Otherwise, it looks pretty much like the same theory. They both behave the same way. Electric dipoles move toward increasing fields once they rotate as well. Okay. All right. Back to our example. So we're going to attack this. The first thing we have to kind of grapple with is how do I find mu for a disk? Mu is only defined for a hoop, right? But if you think about it, what is a disk? A disk is made of a bunch of thin hoops. All of those hoops sort of spin, and each of those spinning constitutes some amount of current inside of each of those loops. And so if you want to know how much current lives right here, you say, well, how much charge lives there, and how long does it take for the charge to go all the way around the loop? In other words, current is Q over T. And I'm saying how much current? Well, DI. And how much time? It takes 1 period for all of that charge to go all the way around. If I want to know how much charge, it's the normal, sigma dA, and then the period is just 2 pi over omega. So this is really not such a big upgrade for this problem. We can say that dI looks like this once we punch everything in, and then if you want to know d mu, you just say it's the area times I. In other words, each hoop or loop contributes some small amount to the total magnetic moment, and if I want the total magnetic moment, then all I have to do is integrate. And so if you integrate this, you end up with this. The only other thing you might wish to do is to trade out the sigma. So remember, Q equals sigma times A. And so if you make that substitution, here you've got a pi r squared. If you make that substitution, you end up with something like this. So it's interesting. Now I have a formula for a magnetic moment that depends on charge and how fast that charge spins, which is just another way of talking about what the current flowing through this disk is. Anyway, the first question we have is how much torque is going to be created on this loop? How is it going to rotate? So we know that in general, the magnetic moment will rotate so that it aligns with the magnetic field. In other words, it's mu cross B. And if you point your fingers in the direction of mu and you curl them toward B, your thumb will point in. The torque is in, which means we're going to rotate clockwise so that we align with that B field. If I multiply my magnitude of my magnetic moment times the magnitude of the B field, they make a 45-degree angle. So what I've done here is I'm just saying magnitude of mu times magnitude of B times the sine of the angle between them. The z hat direction is given by our right-hand rule. Okay, so that's our torque. Now let's continue along these lines before we talk about non-uniform fields. If I want to know how fast it's rotating, here's a bonus. Let's find how fast the loop is rotating once it's aligned with the field. Well, I can find the initial energy. The initial energy is minus mu dot B. The initial angle between mu and B is 45 degrees. So just recall this is mu times B times the cosine of the angle between them, which is 45 degrees. When they're aligned, the angle between them will be 0. And so if I want to know the difference in kinetic energy, that's minus the difference in potential energy. So that's U initial minus U final. So I had a minus delta U. That's why I swapped the initial and final. And okay, this is how much rotational kinetic energy this thing has. If I wanted to know the rotational speed it has, I could do moments of inertia and all that stuff, but that's not really the focus of this video. It's not a big deal to upgrade though. Okay, so now I know the magnetic moment of the loop, and the thing I want to know now is if the disk is very small, let's find the force it experiences from another dipole below it. So this is really a question about a non-uniform field, okay? So the magnetic field that dipoles create is given by this. I'll work this out in another video. For now, you can just take my word for it. Crucially, though, notice that this is not a uniform field. It depends on the distance y between them. And this is only the field on axis. Off axis, the field's a mess. But on axis, it looks something like that. Okay, and notice it is given in terms of the magnetic moment mu prime of this lower loop. So the lower loop makes a non-uniform field, and my disk from earlier feels that non-uniform field, and first it rotates so that its magnetic moment is aligned with the magnetic field it finds itself in, and then I find the force first by finding the potential energy, so that's mu dot B. So remember, the B field is created by the dipole beneath, and this mu guy feels it. So they're already aligned. The angle is 0, so I don't need a cosine theta. And then if I want the force, I simply differentiate. So we say Fy is minus du dy. Notice that if I take a derivative, there's a bunch of minus signs here. Look, if you differentiate this, you pick up a minus. There's a minus here. But what we end up with at the end of the day is something that is negative, which means it points downward. And what that means is that these two loops will be attracted to each other and they will end up making a larger dipole. They'll kind of combine forces and they'll make something else that has some larger dipole moment. The reason I say the dipole moment grows is because their dipole moments were aligned. They rotated until they were aligned. This is exactly what bar magnets do. If you put two bar magnets at some weird angle relative to each other, first they'll rotate and then they'll connect. And now it's as if you just had one larger magnet. And so these little loops behave the same way because this is nothing but a collection of little loops. Okay, hopefully this video was more helpful than confusing.